You should be able to stream.
Now?
You are live.
Hello, everybody. Sorry we're a little late. Had a little technical difficulties. My name is Jerry Chevrier. I'm a NASA Solar System Ambassador for Southeast Michigan. There's several of us in Michigan. If you ever have an event that you want, Boy Scouts, I do schools, we do colleges, we do all kinds of things. So if you're interested in astronomy, you can get a hold of me, or I also belong to the Oakland Astronomy Club that does events. We have several telescopes, so things like that. I want to put a little plug in for NASA. I usually, if I'm in a crowd, I'll ask people who knows what that stands for. There's probably maybe 2 or 3 people in the crowd that would know. It's the National Aeronautical Space Agency. And so if we have any kids on the line, you want to stay in STEM research, which is science, technology, engineering, and math. And you can probably, I don't know what age you are or if there's anybody in the crowd, but NASA's going to be needing astronauts for both the moon project and to go to Mars. So this is a great time if you stay in those math and science classes. And as you go to college, when you graduate, think of working for these guys, because I would think that would be very, very exciting. So my topic tonight is neutrinos. And the reason I got excited about them, actually 6 months ago, I didn't know anything about them. But we want to talk about them because it's really a dynamic, expanding field in astrophysics and in astronomy, and we'll go over what it is. So we're going to talk about what are they, where they come from, and a really cool part I found when I went and did my research on this is how do you detect them? And I think you're going to be blown away because of the money we're spending on trying to detect these particles. It's an amazing story. So I got excited because of supernovas. When supernovas are stars, and usually our star is a medium star, but when there's stars, 100 to 200 times bigger than ours, when they blow up or go, we call it supernova. When I read that they put out 99% of the bursts in the first 10 seconds are all neutrinos, I didn't know what a neutrino was, so I kind of dug my heels in, and so I'm going to go figure this out. So one of the interesting parts of supernovas is that in our galaxy, they only happen once every 10 to 50 years. And the last one that happened was in 1987. And we're going to be talking about neutrino capturing devices on the Earth, but we caught a bunch of neutrinos and detected them. And I'll tell you why that's important. So again, supernovas put a lot of neutrinos out. And at the time, I didn't know what they were. I'm not a physicist, but it's kind of interesting that a neutrino is actually a building block or a fundamental particle. And that means, in layman's terms, is that you can't break it down anymore. So if you look on the bottom left, you've got an atom, right? And we all know from high school or even in grade school now that there are protons and neutrons and electrons, right, in those atoms. But a proton gets broken down into quarks. And so 2 quarks, make up a proton, and 2 quarks that are D and 1 quark, you make up a neutron. So those quarks are fundamental products. So if you go up into the fundamental products, up on top, there's 12 of them. And quarks are the second one down. So there are different types of quarks. But the big arrow, if you take a look at the big arrow there, those are neutrinos, okay? And there's different types of neutrinos, and we'll talk about that. So a neutrino is a fundamental particle, just like a quark would be, if that makes sense. I found it pretty fascinating myself. Here's the part that I got excited about. I know a lot of people don't get excited about neutrinos, but I did. 100 trillion of them go through you every second, and they're mostly from the sun. And there are 3 different types of neutrinos. There could be more, but as of today, we've found 3 of them: an electron, a moon, and a tau. And there's different. Think of it as ice cream. 3 different flavors of this neutrino. And so a neutrino really comes from a nuclear reaction, and it decays and becomes a neutrino. And that's where we're getting so many from our sun. If you remember my first slide where they had, I know this is just me kind of thinking positive, but can you imagine if we could somehow harness 100 trillion neutrinos going through you every second, and we could somehow make them become energy or something like that? It would be fascinating, but we're so far off from that. But one of the things that we are finding is that if you look at, I'll tell you why I think it's important and why we're spending so much time and trying to understand. Well, we understand particles, but a neutrino. If you take a look at our universe, not just our galaxy, our entire universe, that means all the galaxies, right? We're in the Milky Way. So in those galaxies, of all the light and all the light that you see, the stars, the nebulas, planets, all the things we see only make up about 5% of the universe. So when I first started getting into astronomy, that kind of blew me away. And so the other 95% is dark energy and dark matter. And we need to understand what that is if we're going to continue in our space exploration, I believe. And so I believe that neutrinos will help us to understand black matter and dark energy better. So neutrino was first conceived, not even found, in 1930. And then they were detected in 1956. And the guys that detect them are here on the page. And because of the importance of it, because they found a new particle, they got the Nobel Prize. So this is pretty interesting stuff. And then in 2002, again, they've won the Nobel Prize for the study of neutrinos. And these guys got it because they found that those 3 different flavors, as I call them, of neutrinos, they were able to detect them. And in 2015, again, 2 other people got the Nobel Prize. So you can see that a lot of people are spending a lot of time in trying to understand neutrinos. So again, I'm just going to summarize here a little bit. 3 different flavors of neutrino. It's a fundamental product. That's what the word fundamental means. And they're abundant. There's so many of us going through us. And they're very hard to detect. And we're going to find out what it takes later on in this presentation to detect them. But they are very light in mass and in charge. So since there's 100 trillion going through every second, it doesn't affect our body because there's not a big charge or there's not a lot of matter. But they're very hard to detect, and we're going to go over that. So where do they come from? Again, I found this an interesting slide because, again, I'm hoping that one day we can somehow have enough technology to harness these things, these neutrinos. You imagine having a little device in your house that provides all the electrical. So they come from, I've got some kind of noise going on. I hope it's not bothering anybody else. They come from cosmic rays.
But as soon as I get it in,
Is this new?
the telescope isn't, but basically we're running
You guys hear me too?
4 sessions simultaneously. It's the astronomy at the beach is it's a big event. It normally is out at Island Lake State.
Hello?
but this year we're doing it all virtual. So yours truly set
Okay.
it up, and people don't.
I'm going to keep going, and hopefully this other
One guy's coming a
conversation
half
goes
hour
away.
late. It's like, guess what?
Um,
I'll use one
so
license.
neutrinos
and
come
if
from
we go over,
cosmic
that means
rays,
everybody's got to be shifted.
and they're again from nuclear
They're all
reaction,
trying to follow the schedule.
and they travel at the light speed of light.
No, it's never
And
happened.
so one of the nice things about our Earth in that slide, that little, there's the sun, and that little thing there is our Earth.
It literally is like,
And the reason we get
beyond myself, my own
kind of
distinction.
shelter from the sun's solar rays is because we have a magnetic field, and that's that little thing that's shooting.
All right.
When the rays come out of the sun, they go around our planet. And so, but some of the cosmic rays, the neutrons, they don't get affected because they go through anything. So they go right through the Earth.
Cool.
If the Earth was all lead, they go right through it. That's how hard they are to detect. So they come from cosmic rays, and from the sun is the biggest one for us. It takes like 8 minutes, 8.5 minutes to travel from the sun to the Earth. So you have neutrinos. And what's interesting about neutrinos, these particles, is that they can leave the sun in electron mode and end up in a tau mode in flight. So it's like going into the ice cream store and getting strawberry, and then by the time you get home, it's chocolate. So they change in flight, and that's what one of those guys, the last one that got the Nobel Prize, that's what they got it because they detected these 3 different flavors. And so neutrons come from cosmic ray, they come from the sun, but they're born in nuclear fusion in the sun, and cosmic rays are nuclear reactions. And so when they come from the sun produces neutrons, neutrinos. So where else do they come from? Well, there's nuclear reactors and to get electricity, and neutrinos are generated by them. And then the bottom one, actually, we were kind of laughing about this, not laughing, but it was kind of amazing back in the 50s when we were, lighting off these atomic bombs on Earth and underground and in space. But they're also created from a nuclear reaction because that's exactly what a nuclear bomb is. So neutrinos are created by, again, radiation, decay, and radiation. So how do we, and the other thing, they come from cosmic rays, the sun, but they're also, we can make them by these laboratories that we have. One of them is the Fermi National Accelerator Laboratory in the United States, and it's off to the left there. So you've got these gigantic underground beams, lasers that are breaking the atom, and they can create neutrinos in these labs. And then one of the cool things that's happening within the United States anyway is the Fermi lab. And the bottom picture off to the right, you can see the Fermi lab. And then Stanford Underground Research Facility they're going to be shooting neutrinos from Fermi to the Stanford Underground Research Facilities underground. And so you can see the map. That's a long way, but from a neutrino, that's nothing. So they go through everything, hard to detect them, and they're trying to do analysis on neutrinos and how they act, and so we can create them in these laboratories. So Stanford Underground Research Facility is in South Dakota. It's the deepest underground laboratory we have in the United States. And one of the things you're going to find out, to get neutrinos, to detect them, you've got to be underground. You got to be in a cave of some sort, and it's got to be filled with water. So as these neutrinos are coming from either cosmic rays or from the sun or from something created, the only way you can detect them is if you have large bodies of water. And when I say water, there's different types of mixtures of that water, but water, so they light up. And I'll show you that in a minute. And then the Fermi Lab is, again, a particle physics accelerator laboratory. And again, Fermi Lab conducts experiments on particles. And I'm not going to get into it a lot, but if you're ever out that way, that would be a fascinating visit. The largest one in the world is here, the European Organization of Nuclear Research. It's between France and Switzerland, near Geneva, Switzerland. And I just think that's fascinating looking, just the outside of it. Yeah, but it's the largest one in the world. And it employs about, 3,200 people, all Europeans, with the exception of Israel. I don't know why that is. And it started up in 2008. It's 16-mile ring. And again, this is the largest in the world for doing particle research, but they can create neutrinos in this facility. And I'm not going to go through every country because most universities in most countries have research accelerators like this to do research in particles. I'm not going to spend a lot of time on it, but Japan has one. And it's a complex that, for their science labs. Not as big as the one in Europe or Fermi, but Japan has one. So how do we detect them? This is they're so hard to detect that they're 100,000 times smaller than an electron. And you know how, and they call them ghostly neutrinos because, you can't see ghosts, right? But they very, very, very small. They don't have much of a charge, very, very, very little, and they don't interact with other atomic particles. So they're just flying through space, through the worlds, and at the speed of light. So again, you have to build underground water tanks. And I'm going to show you some of them that are around the world. And that I found pretty fascinating too. So neutrino detectors. One of them is in the Mediterranean Sea off near France. And you can see what they do is they got these lines that go into the water to the bottom. And as the neutrino goes through the water, those little bulbs that are there are trying to detect them, and they would detect the neutrino. So this is a small one actually. The one that really fascinated me is ours. Of course, anything we do, I get fascinated. And it's called the ice cube, and you should Google this sometime if you have some time. It's in the South Pole, and they drill. I'm going to show you pictures of it, but they did it in 2013. They had a breakthrough of the year with a cosmic. They detected, again, not a sun neutrino, but a cosmic neutrino coming from a cosmic ray. So ice cube, Google it. So you're pretty isolated at the ice cube. I mean, look at the auroras there. I mean, it would be fascinating to be there for about, I don't know, a week. Then I want to get out, but once you get there, you can't leave. And it's headquartered, it's ran out of the University of Wisconsin. And they detect about 275 neutrinos daily and about 100,000 per year. So if you think 100 trillion going through you every second, that's pretty hard. That's not detecting a lot of them because they're hard to detect. So this is the plane you go there in. So you can see in that very short window that you're able to get there. But it would be fascinating to be there. But once you're there, you're going to be stuck there for quite a while until it gets nice enough for the plane to come and get you. So this is up to 1.5 miles. They dig a hole into the ice and they put these, I'll show you what they are, but this is call them lines going down into the ice. And this is a picture of the ice cube. On top is that little blue thing's the ice cube, the building. And then, you know, they got 86 strings and they're 125 meters apart, and they string them all down into the ice and then into the water on the bottom. And they put, and you can see off to the right on top, if you know where South Pole is, it's, you know, it's pretty cold. So they got these detectors drilled into the ice, all this just to detect neutrinos. This is what's stringing on them. They're called DOMs, they're light sensors. And so each of the strings, you attach these domes, I just call them dome, digital optical modules, and they sense the neutrino coming through the water, and these would light up and detect them. I'm not going to go into this, but little sophisticated little device. And then as the neutrino goes through the water and gets detected, it light up and get detected. Here's the next most interesting one to me. The ice cube was fascinating to me because it's the United States, but Japan has this one and they're building one even bigger. So there's a lot of money we're talking about here, building these things just to understand this particle. So this is the super Camdini, or I don't know how to pronounce it, but started in 1996. It's got 50,000 tons of water. And take a look at the boat. I mean, there's a little boat there, and they're all going along these DOMs and either fixing them or adjusting them. And this is the guy in 2015 from this facility were able to detect the neutrino in 3 different flavors, and they got the 2015 Nobel Prize. So you could see the work and the effort going into just detecting these things. And this is they're building now. You remember the last one I showed you, it's 50,000 tons, right? This is 260,000 tons of water. And again, it has to be underground. And the reason they're underground is because as rays come from the sun onto the earth, they don't want anything interfering with their detection, number one. So get underground. And then 2 is because it needs to be filled with water to even detect them. So this is being built, and it starts in the 2020s, which I'm thinking, I don't know if it's 2021, but if you Google this facility, it's pretty fascinating how large this thing is. And then can't count out the Chinese. I don't know if you know, this year that the Chinese last year they went to the moon, the dark side of the moon, not with people, but with a probe. And this is a year that they're all going to Mars, China, us, actually United Kingdom, the Arab United Kingdom, and the European Space Agency. There's 4 countries going to Mars. And I'm kind of getting away from the neutrinos for a minute, but China is becoming more and more engaged in space and research. So here's theirs. This is called Juno. It's 700 meters underground. Again, everything's got to be underground, and it's got 20,000 tons of, and I call it water, but it's actually liquid. There's different things that are mixed in there, but fluid. I should probably call it fluid. And so they're spending a lot of money in understanding and detecting and getting a better idea of what a neutrino is. And then I'm not going to go through each of these, but Canada's got one. So you can see as I started looking into what a neutrino was, and then the money being spent to understand it, it's a big booming field of study right now. So Australia's got one, and then Russia, can't count Russia out either. Russia's got one. So you could look at these if you want to. The one I found the most fascinating is Japan's, because of how large the next one's going to be, and then the ice cube.
Might not get to it right away, but
I'm thinking of you.
thank you.
So I'm going to end mine with a joke. A neutrino walks into a bar. A neutrino and says, "What can I get you?" And nothing. I'm just passing through. Someone's got to laugh. All right. That's my presentation. I don't know if I can take questions or not. I guess not.
What's that? Sorry.
Well, that's all right. I just didn't know if anybody had any questions. Do we take questions or?
Let me check I haven't been able to pay attention to those.
Okay.
Let's see. Actually, we have no questions.
Okay. All right.
But we had 19 concurrent viewers
Okay.
so far. So
Well, I'm glad.
are you all set?
I'm all set.
Okay.
I hope I generated some interest in neutrinos. I found them fascinating.
Yeah, it sounds interesting.
All right. Thanks.
Yep. Thank you. Okay. End stream.